All right, welcome back. So hopefully everyone had a good reading week and actually slept at least a day. A day. That's pretty good for engineers.
Is a quiz this week or next week?
I think it's next week, right? But we can go over page table stuff because there's only like not that many people last Thursday. People kind of forgot about. All right, so today we're going to talk about basic memory allocation
Sorry. What's the quiz on?
on all the content. So the quiz will mostly be like scheduling, page table replacement, page replacement, page tables, scheduling, memory allocation. So let's talk about some basic memory allocation. So hopefully this is kind of review. There's a few strategies you can use when you need memory. So static allocation is the simplest thing. So you just create a fixed size buffer in your program. So like char buffer 4096. We know that number is special now because that's the size of a page. And you just declare this like at the top of your program, and then whenever the OS loads your program into memory, part of the process of it loading it to memory is this will actually be allocated some space, so it would be backed by a physical page, and then you can go ahead and use that memory for the duration of your process. So you don't even have to free it, so it lives as long as your process lives, and then whenever your process dies, then that memory is freed because all the resources associated with your process are freed whenever you get acknowledged as your parent. And hopefully everyone's being good parents in Lab 4. So that's what happens. Program loads, kernel sets aside memory for all your like global variables. So if you threw static in front of this, nothing's going to change. Yep.
For Lab 4, or just in general, how can anything but the OS know if you didn't wait on your children?
So the question is for Lab 4, how does anything but the OS know if you didn't wait on your children?
Your tester, like, are you able to tell if we waited on our children? Like, I did, obviously, but if we didn't wait on our children, how would you tell that?
So the tester works, one of the tests of the tester, it S-traces your program.
Oh, okay.
So it counts the number of times you fork and counts the number of times you wait.
I see.
So otherwise it wouldn't be able to know, but I'm looking at your system calls for that. So also some creative solutions for Lab 4, do not put read and write in your program. It's very, very wrong. The Lab 4 primer was just how to use the APIs. If you read the spec of the lab, it's a completely different problem. So don't like blindly copy. Blindly copying is bad. You'll be using pipes. That's about where the similarities stop. You need to use pipe, you need to use dupe2, you need to use close. You don't need to use read and write. We were just showing how to communicate.
Wait, isn't that what you did in the video? You just demonstrated.
Yeah, it's a completely different problem though.
No, in the demo you didn't do read and write.
Yes, I did.
Oh, you mean I know.
Yeah, so remember the Lab 4 primer? I made a child process. I had two pipes. I used one to send data to the child process and one to get data from it. So I had two-way communication. I was sending data and then getting data from it. Lab 4, you're just connecting things in a single one-way communication channel. The pipe just flows from the first argument to the last argument. Okay, where was I? Yeah, okay, sorry, back to this. So this is static allocation, exists as long as your program exists, nice and easy, don't even have to remember to free. But often you need dynamic allocation. So you may only conditionally require memory. Static allocations can sometimes be wasteful. You don't always know how much memory you need ahead of time, and while you're running, things could change. So I don't know, even if you're programming a game or something like that, you could be like, well, at most there'll be like 100 characters on the screen. So I have a global variable that can hold up to 100 characters, but then after 100 characters, you don't have any more memory, so you can't really do anything at that point. So you generally want to use dynamic allocation if you don't know the size for things ahead of time, because if you do, static allocation, you can't change it after your program loads. That's just what it is. You can't request any more memory through global variables or anything like that. So then the question is, well, how do we allocate memory? So hopefully we're used to this now, although you might not know the mechanism that the compiler uses to actually allocate memory for you on the stack, but you either allocate memory on the stack or on the heap. So stack allocation is mostly done for you in C, which is why we basically use C instead of assembly. It is a bit nicer than assembly. So if you think of a normal variable just in a function, you have int x or something like that. Well, that's 4 bytes. So that's going to be allocated 4 bytes on the stack. But what you don't know probably is that there is a special function call the compiler inserts for you, so you don't actually have to write that, called alloc_a, not malloc. So alloc_a will allocate memory for you on the stack. So, and it takes an argument, which is the number of bytes to allocate. Yep.
So if this thing adds it onto the stack for you with all the codes, why don't we just use alloc_a instead of malloc when we're making our dynamic stuff?
Sorry, why would we use alloc?
Why would we use malloc instead of alloc_a?
So the question is, why would we use malloc instead of alloc_a? Anyone else want to answer that? No, you can ask for a number of like different size memory on the stack if you want.
Yeah, but why would you do that?
Why wouldn't you?
No, but the stack is for static things, right?
No. The stack's dynamic. It just grows.
Oh, right, because it's only defined in this reference frame, in this like stack reference, right?
Yeah, so alloc_a allocates memory for you on the stack, and malloc allocates memory for you where? On the heap, right? Completely different places. Sorry?
You're doing 4 because that's the size of it, right?
Yeah, 4 is size of the int. So alloc_a and malloc have the same kind of API. It's the number of bytes you want. So this is like internally, that's what the compiler is going to do. If you ever have the fortune of reading LVM code, you'll see alloc_a all the time, and that is basically just the stack allocation. But the nice thing about alloc_a is when you have malloc, you have to free it. If you have alloc_a, you don't have to free it. So whenever the function that has the alloc_a returns, all the memory is freed because all it does is restore the stack pointer, which is also really nice because it's super, super fast. So no matter how many things you alloc_a, it's only one operation to deallocate everything because you're just moving that stack pointer back to the beginning and basically undoing every single stack allocation. So all it does, one allocate, it's really, really fast to deallocate stuff, but you're kind of stuck with this lifetime. Yep.
When you're deallocating, you're not actually like changing the data. The data is still there, it's just not.
Yeah, so the good question is, when I'm deallocating for stacks, I'm assuming, I'm just changing the stack pointer, I'm not changing the data at all.
So in theory, you could like return the number of like some pointer somewhere and still access that data. It's just you don't have any like proof that it might not also be accessed by other things or something like that.
Yeah, so your question basically is, what if, basically if I make a silly example of it, say I write a function that returns a pointer. Let's call it foo, because who wouldn't want to call it foo? I'll allocate int x, something like that, so that's allocated on the stack. And then if I go ahead and do something like return address of x, and do something like that, then that's bad. So at this point here, whenever you call foo, it's going to allocate that on the stack, so it's going to push the stack down 4 bytes and return a pointer to that, essentially. And then in your return, you're giving that pointer away, and as soon as you hit return, that's the end of the function, so that deallocates that x. So now it would just reset that stack pointer, and then you would be returning an address to the stack that is no longer guaranteed to be x because x doesn't exist anymore. So likely it's going to just be if you use it straight away, you might be lucky and it might still be the value of x. Like if I wrote x equals, I don't know, if I wrote x equals 42, maybe you get lucky and it's 42. So if I had, say we had main, and I declare, hey, p equals foo, well, maybe I get lucky, and if I, read the whatever the value dereference p, maybe I see, I actually get 42 out of it. But if I call another function, bar, I don't know what that's going to do with the stack. It probably will go right, probably have its own values. And then if you dereference p here, well, this could be anything. It's probably going to be some leftover garbage with whatever bar used to do that. So you don't really want to do that. So does that make sense? Because that will definitely give you weird errors. Yep.
So as soon as you go to another stack frame, this just disappears even if you come back?
So like the address, so p will be a pointer to somewhere on the stack that, is a bit further along than main. So like main, so let's say it goes up. So main will be here, it'll have some room. There'll probably be space for p at some point. And then whenever I call foo, it has, some other extra information than x. And then I return a pointer that points here. And then foo returns, so all this gets reset, but the pointer doesn't change. I'm still pointing at something way off in the distance. And then bar could execute. Say bar is bigger, and it uses the variables like a, b, c, something like that. That could be pointing at like a, b, c, who knows.
Oh, so after a return, the value of 42 is still there, but like it's not guaranteed to be there afterwards.
Yeah, it's probably still there because I looked at it directly after returning, and you're not.
It's no longer like it's no longer like reserved.
Yeah, it's no longer reserved.
Okay.
So you have no idea what it, like, whatever reserved is long dead by now. Like we returned from foo.
Wait,
So,
but if you don't have a bar, is it guaranteed to be 42 or something? You might just keep executing. Like if
yes.
it's another local, it might overwrite that location. So probably no.
Yeah, I mean, if you allocated, say you like allocated another.
No, I'm saying if you don't do any of that stuff.
Oh.
Just do start PM2.
Well, if you don't do anything, your program's done by that point, so you can just exit. So, But yeah, I mean, you might get lucky. If you read the C spec, you're not allowed to do this at all. It's undefined behavior because maybe you have like a secure version of C that like wipes the data when it undoes the stack so that there's nothing left there. So implementations are actually allowed to do that, but it's slow, so no one's going to do that. But according to the spec, you're allowed to do that. So that's why you have to be careful with C. Anything undefined in the spec, that's free for them to do whatever you want. And this is undefined in the spec.
So,
Yep.
are there multiple people organizations that are like making different variations of C that all like meet the same specs, but maybe do other things to meet those specs?
So the question is, hey, are there a bunch of people basically implementing C and doing the unspecified things in different ways?
Yeah.
Yes, of course.
I thought there was just one global institution that did C. I don't know why.
No, so you've like the Microsoft C compiler, you've GCC, you've Clang, so that's 3 compilers.
And they're all different organizations.
Yeah, well, it's just different people writing them. And the Microsoft one does very odd things. So anything, yeah, I've debugged student code that only had errors if you compiled it with Microsoft's one, because Microsoft does some real crazy stuff. The Microsoft compiler is not great. Okay, so this is stack allocation. So you've also used dynamic allocation before, so on the heap. So these are the malloc family of functions, and this is what we're going to talk about how they're implemented. So this is kind of the most flexible way to use memory, but also given the number of seg faults we've all done in our life, probably the most difficult to get right. So you have to properly handle your memory lifetimes and free exactly once. So you malloc once, you're only allowed to free it once. If you free it twice, that's an error. If you never free it, you're wasting memory, that's a leak. So both of the cases are bad. Yeah.
So when you, so in for dynamic allocation with like malloc, for example, if your program is only allocated like 2 pages originally and you malloc more data, the OS could give you another page. Does that also work with alloc? Like say your stack just keeps growing and you want to allocate like more to the stack, could it request another page from the OS?
Yeah, so the question is, if I run out of room on my stack, can it just request another page? Generally, I think it works the same way as pthreads, where your stack is a set size. So the most your stack will grow is to 8 megabytes.
And if it grows more than that?
Stack overflow.
Okay.
Yeah.
So it's given, originally, your program is given the 8 megabytes. That's the smallest amount it basically has.
That's the most.
Oh, but so it could get less as you keep requesting more pages up until 8 megabytes.
Yeah, so if you get into the details of it, so your stack will be given like 8 megabytes of virtual address space, which is all deemed valid, but it'll only back it by pages as you're actually using it.
Right.
So if you only use like 4 kilobytes, it'll only be 4 kilobytes. But as soon as it goes above the 4 kilobytes, the OS there'll be a page fault, and then it'll just grab another page because it's supposed to be valid.
I see.
And then as soon as you go over 8 megabytes, it'll be Stack Overflow, which is also everyone's favorite error. But probably you've got it less in this course. Yeah, has anyone ever got Stack Overflow so far in this course? Probably not, right? Yeah, so we eliminated a class of bugs. Yay. Yeah, so malloc. So there's also a new concern if you're implementing malloc, and that is fragmentation. And again, fragmentation is basically wasted space. So this is a unique issue for dynamic allocation. So since you allocate memory in different size contiguous blocks, or at least it looks contiguous because it's all virtual addresses, you're not allowed to compact anything if you are using malloc. So what compaction is, say you do a bunch of mallocs of different sizes, and say you like have 100 bytes, and then there's like a hole of like, I don't know, like 2 bytes or something like that, and then another malloc of like 100 bytes. Well, that 2 byte hole you might never ever be able to use again, because what about if you only malloc like 4 bytes after that? Well, 2 bytes isn't enough, so that's basically wasted memory that you'll never ever get back again. What you would like to be able to do, if you could move memory as well, that 2 byte hole I'm never be able to fill, so I'll just look at memory and then compact everything so that everything is nice and contiguous again, get rid of that hole. But you're not allowed to do that in C because you're using a pointer, and if you are the memory allocator, you are not allowed to just move memory around because the program has a pointer to it, and it's not going to change. It's just an address, and it's not going to change the address. You have no way of updating the program and be like, hey, I moved your memory, don't worry about it. But if you're Java, you can actually do this, because Java has a layer of indirection because you don't get to touch pointers in Java, so you'd never actually know the value of the pointers. So the JVM's free to move memory around on you because you never get the address of something, so it can move it around. As long as it updates all the references and it's consistent, it's fine. So Java actually doesn't have this problem because it can move memory on you, but it's also why it's slow, because it needs to update all of the addresses to make sure everything's consistent. And you probably won't get into that, but that's just a nice thing to know. So fragment, basically hole in memory that's wasting space, and we need 3 different things to all be true in order for fragmentation to be an issue. So all the allocations have to have different lifetimes, and then all the allocation sizes have to be different, and then we also need the inability to relocate previous allocations. So can someone tell me why I would not have any fragmentation if, number 1, was not true.
So with like different allocation times, that's the question.
So if all the allocations had the exact same lifetime, I wouldn't have fragmentation. Why? Yeah.
Well, since all of them just disappear at the same time, then like you can just start from the beginning again and just fill it out.
Yeah. Is that what you're going to say too? Yeah. So if number one isn't true, then it's basically, they're like stack allocations. So they all get freed at the same time. So I could just allocate them all contiguously together. And then since they have the same lifetime when I deallocate them, they all get deallocated together. So I won't have any fragmentation. And that's why you don't have any fragmentation on the stack, which is kind of another reason you'd want to use the stack. All right, what about if number two isn't true? Why wouldn't I have any fragmentation in that case? Yeah.
Because like as long as if you're say like everything is size 1, then you just like you're doing it basically like integers. And if you have one's missing space, you can always put an allocation in that spot because it'll be like if you're allocating blocks of like 2 bytes, then as long as you're not stupid and you don't allocate it on like the 3rd byte or something like that, you'll always end up with a space of 2 bytes between, which you can always fill with an allocation.
Yeah, or if I go above that, think of the kernel. So the kernel allocates everything in size pages. So if there is a hole, it will be the size of a page, which can fit an allocation because they're all the same size. So I don't have any fragmentation, everything's the same size. So it doesn't matter. So that's why you wouldn't have any fragmentation in that case. And then number 3, you wouldn't have fragmentation because if you can move stuff around, you can just move stuff around to get rid of the holes, which is kind of what we discussed with what Java does. So those are your 3. So all of those have to be true in order for fragmentation to be a problem, which if we try and make the most general solution of making a malloc, then these are all true. So malloc can't move stuff, malloc has to handle different allocation sizes, and then malloc has no idea what the lifetime is. You can't predict when someone's going to malloc and then free it later. And given some of the things we've seen, you might never free it as well. Okay, so there's actually 2 types of fragmentation. There is internal and external fragmentation. Basically, the memory allocator just cares about, does allocations in blocks of memory, and that's all it cares about. So external fragmentation is when you allocate different sized blocks, and then there's no room for an allocation between 2 blocks that it already allocated. While internal fragmentation is an issue with some memory allocators. So some memory allocators might allocate fixed size blocks, maybe to get rid of the fragmentation issue or one fragmentation issue, but there might be some fragmentation within the fixed size blocks. So in this picture at the bottom, there's 2 blocks there that are managed by the memory allocator, like the bigger blocks, and then there might be wasted space within a block. So say, hey, my memory allocator is not going to have any fragmentation because all my blocks are like 64 bytes or something like that. Well, you still have to deal with the case of you get a allocation for like 40 bytes and one for 10 bytes, in which case you would allocate the 64 byte block, but 22 of those bytes would be wasted internally within that block, and only the 40 would be used. So even though you can get rid of some fragmentation, there would still be internal fragmentation. So we'll see that next lecture when we get to more specialized memory allocators, but we'll just keep it general for now. So for now, we're only going to have external fragmentation because we're just going to match, our allocation is going to match whatever the size of the request is that comes in. So our goal, basically we just want to minimize fragmentation. So it's just wasted space. We want to prevent that because it's just memory we're not allowed to use on our system, which is bad. I don't want to see a out of memory issue if I try to allocate, a gigabyte and I know I have like 3 gigabytes left. If it just says out of memory, I'm going to be like, what the hell, this operating system sucks, and then switch to something else. So we want to reduce the number of holes basically between blocks of memory, which is our fragmentation. And one of the ideas you might have is if we have holes, well, maybe I'd want to keep them as large as possible, and that way I can just use that hole to do more allocations, so that would be cool. So I want to just keep allocating memory without wasting space. So when you go to implement these allocation strategies, most allocator implementations actually just use a free list and keep track of the size of the blocks that it issues. So it keeps track of the free blocks of memories by just chaining them together in a big linked list. And we know we need to handle a request of any size. So for an allocation, we would just choose a block that's large enough for the request, remove it from the free list, and now it would be used. And whenever we have to deallocate something, we just move the block back to the free list, and then we can reuse that. And if it's adjacent to another block, so like there's two free blocks right next to each other, we just merge them together and make one big free block. Mm-hmm.
Your linked list is cost memory.
Yeah, so the allocator would need a linked list, which would cost memory too.
But how do you keep track of that, like fragmentation of that memory?
So some implementations will put basically the list information and accounting information before the memory that it gives back to you, which at least one of you on Piazza like corrupted Malloc's internal structures. So that's what happened there. So it writes some information, accounting information. If you look at malloc, the memory it gives you, if you actually just write random bytes right before it, you'll screw up its accounting information, and then malloc won't know what to do.
Wait, how do you do that?
So whenever you malloc something, you get a pointer, right? Just like subtract 2 bytes from the address and just change the value to something. You're allowed to do that. It won't segfault because that memory is used by malloc to keep track of all the free blocks and everything. So if you just write random information to it, it's going to get very confused. So at least one of you has done that accidentally on Piazza, because I saw some post where it's like, yeah, some weird internal malloc error where it's like, yeah, this doesn't make sense anymore. So yeah, if you want, you can look at, so there's different malloc implementations too. Some of them might not do that. I believe the default one does do that, but they're allowed to keep the bookkeeping information wherever it wants, but some reuse the memory, which is kind of cool. So in general, if you're implementing malloc, there's kind of 3 general heap allocation strategies that you can use. The first one's called best fit. So I basically choose the smallest block that can satisfy the request, which of course means I have to search through the entire free list. So unless there's an exact match, because if there's an exact match, then I can't do any better, so I may as well use that block. But in general, I'll have to search through every single element to see what the closest block size is. And then worst fit sounds kind of bad. So it chooses the largest block that has the most leftover space and makes it a bit smaller. And again, this also has to search through the entire list. And then there is first fit, which is much easier to implement and doesn't have to search through the entire list. It only has to do that in the worst case. So it basically just chooses the first block that can satisfy the request and uses that immediately and doesn't care how big it is, as long as it can satisfy the request. So to make this a bit more concrete, let's do some allocations using best fit. So at the top there is memory. So let's say our memory allocator is managing this big block of memory. There is a red allocation that we're not allowed to move because we already made it. And then a blue allocation we're also not allowed to move because we already made it. So then the blank space here are the number of bytes that are free. So we have two free blocks. One has 100 bytes in it, and another has 60 bytes in it. Yeah.
Sorry, so in these questions, we don't have to worry about how like these linked list memories are managed, right?
Yeah, so for this, I'm not showing the details of like actually keeping track of the free list. We're just looking at it. But if you were to implement it, you'd have to keep track of the free list.
Okay. Wait, how do you keep track of the free list again?
So you'd have a linked list somewhere in your program.
Oh, that's it?
Yep.
No, but I'm saying doesn't that cost memory too? You don't have to worry about them?
Yeah, so you'd have to allocate memory for yourself too.
But how do you worry about that kind of specific allocation? Like, cause that to implement a linked list, you need memory, right?
Yeah.
How do you know that's like small or large? That doesn't affect the rest of it.
So malloc is managing the heap, so it can grow it as large as it needs. So it can use some of the heap space for its own linked lists and things like that.
Oh,
Yeah.
But like off this point, if malloc itself here is trying to figure out which blocks to use to allocate for different allocations, but itself is using itself, like it just seems circular. Like malloc needs to use itself to allocate, but it like can't do that without it using itself. Like I'm just kind of confused by that.
So malloc, there should just be a lab that you have to implement malloc. But malloc, what it could do is just have a global variable that's just like the head pointer of the list. And anytime there's an allocation, it would create a node basically, and then it could point to the node and say, hey, that one's used, and then have one list for free that, you know, by default, you'd increase the size of the heap and then say, hey, the whole thing is free minus whatever I need to keep track of it. And then you just do allocations from there. And then every time you allocate something, you just add a node to that list with some of the memory.
Oh, and the nodes could all be the same size too.
Yeah, the nodes would be the same size.
So then it no longer, it doesn't have the fragmentation problem.
Yeah.
Okay.
Yeah, so all your nodes would be the same size. So you need to keep track of, for every allocation, you need to keep track of a pointer. You need to keep track of how big it is probably and things like that. So that's like what, like 16 bytes at most? So every allocation is going to weigh 16 bytes. Yep.
So essentially, the free list is just like a list of pointers, pretty much like of like the free blocks.
Yeah, it's just telling you what memory is not in use in the heap.
Like how would that be represented exactly?
So we'd have a linked list somewhere, and it could be in global memory that just is the head of the free list. And then in this case, there'd be two elements in the free list. It'd be a 100-byte block and then a 60-byte block.
So it's like saying this is a 100 byte, this is 60 byte, like explicitly, and then it'll, like when you insert like 48, it'll do like a subtract, like it'll update the
Yeah,
list with like 60 is now 20 or something, or
yeah,
like,
yep.
but is it like, it's essentially like a pointer to like this block of memory, right?
Yeah, but we're not going to be terribly concerned about the actual implementation of malloc, just the general overview without worrying about where you put pointers and where you put nodes and everything like that. Okay, so in this case, the way easier problem is like, hey, say I just have a 100-byte block that's free and a 60-byte block. If I'm using a best fit strategy, well, if there's an allocation that comes in that's 40 bytes, where do I allocate this block? Do I allocate it in the 100 or the 60? 60, because we're doing best fit, so it's the closest one. So 60 is closer to 40 than 100 is. So I would do the allocation in the 60 block, then I have 20 bytes left over. So I have another allocation that comes in, which is 60 bytes in the purple. So where do I have to allocate this block? In 100, right? There's only two free blocks, there's 120. Doesn't fit in the 20, so I have one option. So now I have another allocation that comes in, no one frees anything, and it's in the pink, and it's a 60-byte allocation, and now I'm screwed. So, and this is where it gets really frustrating whenever you use your computer, because it'll do stuff like this. Because we have 60 bytes free, but they're just not contiguous. We have a 40-byte block and a 20-byte block, so we have 60 bytes free. We're asking for 60 bytes, but malloc would fail in this case. Yep.
We can't do something where we just say, here's a pointer to the 40 and here's a pointer to the 20 or something?
How? Yeah, so the question.
Like it'll be hard, but like that way you could use up all the memory.
So the question is, what about if I just return two pointers to the program?
Yeah, or I don't know, it probably would work.
How good is everyone at using one pointer? So how would you, yeah, imagine you just get randomly two pointers back sometimes when you use malloc.
Yeah, so that would work. I mean, malloc itself would have to keep track of the 2 pointers. And they say if you use this pointer and then you go like beyond 40, then actually use the other pointer.
Yeah, and then what about if like half of your numbers in one block and then the other half's in the other block? Then it gets really weird. Okay, so let's go through this example again using worst fit. So now we have a 40 byte block and we rewind, so we have the 100 and the 60 free. So where do we allocate this one? If we do worst fit, in the 100 or the 60? 100. Worst fit, so we are looking for the biggest one. So if we put the 40 in there, we have 60 bytes left over. Now we have the 60 byte allocation. Where do we allocate it? Doesn't matter, they're both the same, they're both 60 bytes, so put it at the front. And now the next block, hey, it fits exactly in the remaining space. So worst fit, in this case, actually does better. So it's not always going to be the situation, but the point is that between just because best fit is called best and worst fit is called worst does not guarantee best is always the best and worst is always the worst, as confusing as that might be. But both of them are both slow. So if you go ahead and simulate this to try and draw some conclusions about it, well, if you look at best fit, it tends to leave very large holes and very small holes. And the small holes might be completely useless, they'll always be fragmented and you'll never be able to use that memory again. While in worst fit, if you simulate it, it's actually the worst in terms of storage utilization, so its name is actually kind of appropriate, even though it might sound like a good idea. And the nice thing about doing simulating all of this and checking is that first fit tends to leave average size holes, and it's also faster. First fit.
Oh, first fit.
Yeah, first fit leaves average size holes, and it's much faster because you don't have to scan through everything all the time.
That's again just like random chains is better than the algorithm you come up with.
It's kind of like page replacement where random is actually better than some of them, than FIFO. So random is actually oddly decent in computer science. So we'll talk about this later because the kernel also has to implement its own memory allocations. So for user space stuff, it just cheats and just does it in terms of pages and kind of kicks the can down the road and says, you deal with it. But the kernel also uses memory, so it actually has to handle its own allocation, so we'll see what the kernel does. But in general, for user space stuff and for the kernel, there's static and dynamic allocations. And for dynamic allocations, fragmentation, if you're actually implementing the allocator, fragmentation is kind of your biggest concern. So there's two types of fragmentation. There is internal fragmentation and external fragmentation. So the memory allocator basically just uses blocks. So fragmentation between blocks is external, fragmentation within a block is internal, and there's basically three allocation strategies in the general case where you are trying to do, where you have any size allocation and you just have the most general problem. So there's best fit, worst fit, and first fit. So any questions about that? If not, we can go back to the page table stuff just in case. All right, no questions, cool. So, just in case as a final call. So hopefully some people around or looked at lecture 23. So is there any questions about when we run this and we do the MMU for this, why the index numbers are the way they are or how this works at all? Or does everyone know how this works? All right, well, hands up, we're good with page tables and everything. Ish? Okay, so let's go through a few questions. So just in case we don't remember, this is a 39-bit, oh God, this cable, virtual address. So because it's a 39-bit virtual address, and our page size is is 4 kilobytes. Well, in that case, since it's a 4 kilobyte page size, that means I have 3 levels of page tables for a 39-bit virtual address, right? Anyone tell me why?
Sorry, what was the question?
So, for a 39-bit virtual address with this page size, the 4 kilobyte page size, I have 3 levels of page tables. Why do I have 3 levels of page tables? Yeah, so remember kind of the trick to multi-level page tables is I try to, each level of page table fits as the number of entries that fit on a page. So in this case, I have 8-byte page table entries. Actually, I'll go ahead and show this. So in SV39, I have a 39-bit virtual address to a 56-bit physical address. I have 4 kilobyte pages, or 4,096. And then my page table entry is 8 bytes. And this is actually what it looks like if you want to get into the nitty-gritty details, is the last 10 bits of it are permissions, like if it's valid, if you can read it, if you can write it, if you can execute it. And then there's 44 bits for the physical page number. And then there's just 10 bits that are reserved for future use. So this makes sense why we have a 56-bit physical address, because 12 of those bits are used as an offset to our page, because that's 2 to the 12. So if we do 56 minus 40 or minus 12, that's 44. So that's our physical page number. So how many levels of page tables we would have if I just told you this information? You should be able to calculate like the number of page tables we need. So if we don't remember it, so the number of levels we need is the ceiling of the virtual bits minus the offset bits minus how many bits we need to index something. So in this problem, how many virtual bits do I have? 39, because that's what it says. How many offset bits do I have? 12. So why do I have 12? Well, because 4,096 is 2 to the 12. So I have 12 bits. How many index bits do I have? Which is a little trickier, but not too much. So for multi-level page tables, what's our little trick we're doing? So each level of page table is how big? Sorry? 512, yes. Yeah, so so there'd be 9 bits. Everyone know why it's 9 bits? So our trick when we have multi-level page table is we want to, each level of page table is going to fit exactly on a page. So I have 2 to the 12 bytes on a page, and then how many entries can I fit? Well, an 8-byte page table entry. So if it's 8 bytes, how many 8-byte numbers can I fit on a single page? So 2 to the 3. So 2 to the 12 divided by 2 to the 3, you can just, we know our exponent math, we can just do 12 minus 3. So it would be 2 to the 9. So we would have 9 index bits to be able to reference everything there. So the number of levels we need, 39 minus 12, which would be, which would be 27 divided by 9, and that's actually a nice division, so we don't need to ceiling everything. So it would be 3. So yeah, so that's a good question. So why don't they just, hey, more space is better. Why wouldn't they do like a 40-bit virtual address?
Because then you need 4.
Yeah, I need 4 page levels. Why wouldn't you do a 38-bit virtual address?
Not using all of your space.
Yeah, I'm not using all my space. I'm just allocating a full page, but I'm only ever going to use half that page table. Why wouldn't I just support more? It's essentially free at that point.
What does PTE stand for again?
Page table entry. So all the page table entry has some permissions, is all you care about, and the physical page number. So
Why do we know it's 56 bits for the physical address? It says 39 for virtual.
so that'll be part of the design, and they'll tell you that. So if you just look at SV39, it says, it's a 39-bit virtual address, and it goes to a 56-bit physical address. So that's part of the design, you'd be told that. In the most part, we don't even care what the number is. If it was it could have been like a 64-bit virtual address if we wanted to, because we have the space, but they just reserved some space because they wanted to. Okay, so that's why we would use 3 levels of page tables, and that's why it's a 39-bit virtual address, because if we only wanted to use 2 levels of page tables, how big of a virtual address could we support? So if we only had 2 levels of page tables, how big would our virtual address be that we could support? Yeah, 30 bits, which is only a gigabyte, which no one would actually use. So basically, we need 3 levels of page table to support anything kind of realistic nowadays, because 1 gigabyte, we're probably going to have more physical memory than that. All right, and why it's 30?
Oh yeah, it is certain.
Yeah, so 30, it would just be 9 times 2 plus 12. Yeah. Okay, so in that case, so let's go back. So in this case, because I know that, that's why I use these indexes. So for ABC, that's my virtual page number. So if I separate that out, so the last 3 hex characters here are going to be the offset. I don't have to really care about them because they're going to stay the same. So if I write out ABC in binary and then divide it into groups of 9, so there'll be your level 0 index, your level 1 index, and your level 2 index are going to be numbers between 0 and 511. And then you just need to make sure that whatever your root page table is, which is going to be a level 2 page table, that entry, you just figure out whatever entry that needs to be at. It needs to point to a level 1 page table. And the level 1 page table, you know what entry it needs to point at. It needs to point at a level 0 page table, and then that has to point at the actual address. Yeah.
Wait, so the offset in this case is only E and F? I thought it was 3 byte offset.
Yeah, DEF.
Oh,
Sorry, DEF is our offset here. All right, so you can go ahead and play with this. If you want, you can watch the end of the section 2 where you should be able to, like, if I give you the address 7 FFF, 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 you should be able to set up the page table so that it actually resolves to like 1 FFF, F. So you can go ahead and do that. That's a good kind of question. So just remember, pulling for you, we're on this together.